Hi, I'm Jay Choi from the Korea AI Safety Institute. In this video, I'll present our work PRISM Video Dataset Condensation with Progressive Refinement and Insertion for Sparse Motion. This is joint work with collaborators at KAIST and Naver AI Lab. Video dataset condensation aims to synthesize a tiny dataset that can train models nearly as well as the full one, cutting down massive storage and compute costs. The core challenge is that in video, content, and motion are deeply entangled. Prior work handles this by disentangling video into a static image and an auxiliary motion signal in 2 stages. But this has a basic problem. The same hand pose could mean clapping, praying, or rubbing hands. Motion cannot be reliably inferred from appearance alone, so we build on 2 ideas. The first is a holistic approach where we optimize the full sequence jointly with no disentanglement. This preserves the natural coupling between content and motion, so we can represent actions that share the same appearance but differ in their dynamics. The second is a sparse approach, where we keep only the frames that truly matter. This dramatically reduces storage costs since most video frames are temporally redundant. This figure compares 3 approaches. On the left, the naive approach updates each frame individually, ignoring interframe relationships, which fails to capture coherent motion. In the middle, the disentanglement method learns motion but is anchored to a frozen static image. This restricts the trajectory and misrepresents how content and motion are actually coupled. On the right, PRISM starts with just 2 anchors, the first and last frame, and fills the middle by interpolation. Then we insert new keyframes only where the motion truly requires it. The result is a sparse, adaptive representation that aligns with the optimal video distribution, with no artificial constraints on either content or motion. Here's how it works. Simple or low velocity motion can be effectively approximated through linear interpolation between keyframes. So, PRISM initializes each video with only 2 keyframes, the start and the end. This minimal initialization is what enables our extreme storage efficiency. Every intermediate frame is filled by linear interpolation between adjacent keyframes using a standard convex combination. The weight alpha t is just the relative position in time. Critically, only the keyframes are trainable. The interpolated frames are updated indirectly through this interpolation, which is what gives us holistic, joint optimization of the sequence. Of course, real motion is not always linear. We need a principled way to detect when interpolation fails. For each candidate frame, we compute 3 gradients, 1 for the interpolated frame itself, and 2 for its adjacent keyframes. The key insight is that when the cosine similarity of the candidate gradient with both adjacent gradients is negative, updating just the endpoints cannot reduce the loss at the intermediate frame. We prove this as a lemma in the paper. That is our trigger. When this gradient conflict occurs, the frame is promoted to the keyframe set and starts being directly optimized. This means representational capacity is allocated precisely where the motion is nonlinear and nowhere else. The video grows only as complex as it needs to be. We add 2 phases for stable training. A warm-up at the start, where insertion is disabled so the endpoints can stabilize before they are used as references. Without this, noisy early gradients would cause premature and redundant insertions, and a cooldown at the end, so newly inserted frames are not promoted too late to be properly optimized. Each phase takes 20% of training, and the middle 60% is for progressive refinement. The pipeline at the bottom shows the full method. We compute a matching loss between synthetic and real videos, and gradients flow only to keyframes, while adaptive insertion is driven by gradient misalignment. With the method in place, we now turn to the results. We evaluate PRISM against core set methods and prior video condensation work across a range of compression rates on Mini-U, CF, and HMDB51. PRISM consistently outperforms all baselines at every compression level. Even at extreme compression around 1%, PRISM still beats competitors that use far more storage. This is the direct advantage of our sparse design, which only stores frames that actually carry information. We also evaluate PRISM on large-scale benchmarks, Kinetics 400 and something V2. PRISM achieves the best or second best results in nearly every setting and the top score at the most aggressive compression of 1 video per class. For cross-architecture generalization, we train condensed data with 1 backbone and evaluate on 3 others. PRISM transfers much better than baselines because optimizing only sparse keyframes reduces overfitting to a specific backbone's inductive bias. We further test PRISM on action retrieval with HMDB51, where it substantially outperforms the prior method across all recall at K levels. This shows that the condensed data captures transferable semantic structure that goes beyond the original training task. Finally, ablations. Starting with just 2 keyframes works best, since more initial frames create conflicting early gradients. Removing frame insertion drops performance significantly, confirming that adaptive capacity is necessary for non-linear motion. Cosine similarity beats L2 distance because direction matters more than magnitude when detecting motion change. Gradient guided selection beats random insertion, so it really is the gradient signal that finds informative frames, not just the act of adding more frames, and both warm-up and cool-down are necessary for stable training. To summarize, PRISM treats video as a unified spatiotemporal structure and uses gradient misalignment to insert frames only where they are needed. The holistic side gives us faithful action representation, and the sparse side gives us state-of-the-art storage efficiency. You can scan the QR codes for the paper and personal website. Thanks for watching.